Good morning, welcome to this next lecture on vibrations of plates and shells. We were looking at a circular plate and we were working through the separable solution in finding the harmonic response or the mode shape. Okay. So, and we were at this stage here. So now if I divide by r and theta, r into theta, okay, so what I will get is 1 over r del 2 del r square r plus 1 over r into big R del r of capital R plus 1 over r square d2 theta d theta square. So these are also d2r dr square d2 dr d small r plus minus lambda square equal to 0. Okay. So now I will do something here. I will multiply the whole thing by r square into r square. So we get r square by r d2r dr square plus r by r dr by dr plus or minus lambda square r square is equal to missed out a theta here, missed out a theta over here, okay, is equal to minus 1 by theta d2 theta d theta square. Okay. So that we set now. Now the main thing here, which is because of Euler, okay, who discovered or presented this form of separation of variables, this side is now purely a function of r, okay, whereas this side is now purely a function of theta, okay, and these two are equal, which means it has to be a constant, and we set it as a positive real constant. Okay, there is a reason for why it has to be so, just a moment. So first we combine this and that. If we do that, we get d2 theta d theta square plus k square theta equal to 0. Okay. So now the important thing over here, why we chose k square as a positive real number, is that this now looks like your spring and mass system whose solutions are stable sinusoids. Okay. If this is a positive real constant and there is a minus over here, or if I chose a minus over here, okay, then these would be hyperbolic functions, either decaying or going off to infinity. Okay, and we don't see that happening. Okay, we don't see that happening, and therefore what we choose is a positive real constant over here. Okay, so now, so the one equation has been figured out. Let's say it's 1. Okay, so what happens to the r part? The r part we again divide by r square, because it's now this term and that term. Okay, what do we get? We get d2r by dr squared plus 1 over r dr by dr plus or minus lambda square minus k square by r square r is equal to 0. Okay. Now, as for the solution of the first equation, d2 theta by d theta square plus k square theta is 0, okay, which means theta of theta will be of the form a cos k times theta plus b times sine k theta, okay, and for plates that are closed with respect to theta, if the plate is closed with respect to theta, that means it's a complete plate, k has to be an integer, k must be an integer. Okay, why? Because the displacement at theta and theta plus twice pi must be same. Okay, and this can happen only if k is an integer, let's say n. Okay, cos n theta and cos n theta plus twice pi. Okay, the latter is equal to cos n theta cos twice pi n minus sin n theta sin twice pi n. So this goes to 0, this acquires value 1 is equal to n theta, but that happens only when n is an integer. So k must be some integer, k is an integer. Okay. Now for the second equation, what do we do? We introduce a new variable. Which is zeta or xi is equal to lambda r for plus lambda square and xi is equal to j lambda r for minus lambda square. Okay, so how does this work out now? We have the r of our equation is d2r by dr square plus 1 by r dr by d small r plus or minus lambda square minus k square by r square into r equal to 0. Okay, so let's see. We said xi will be lambda r for plus lambda square and xi will be j lambda r for minus lambda square. Okay, so if we look at this equation, case 1, if my xi is lambda r, then d xi by dr is lambda, then dr by d small r is dr by d xi into lambda, and d2r by dr square is equal to d2r by d xi square lambda square. Okay, so now if we look at this with a plus, okay, let's do that here. I get d2r dr square, which is d2r by d xi square lambda square plus 1 over r, okay, is lambda over xi dr is dr by d xi into lambda, okay, plus lambda square minus k square by r square is lambda square by xi square into r equal to 0. So you can see that lambda square features everywhere. So lambda square goes from here, and from here, so that I get d2r by d xi square plus 1 by xi dr by d xi plus 1 minus k square by xi square into r equal to 0. That is case 1. Okay. Case 2. Case 2 is xi is equal to j lambda r, which means d xi by dr is equal to j lambda. Then d capital R by d small r is d capital R by d xi into j lambda, and d2r by dr square is d2r by d xi squared into j lambda whole squared. Okay. Now if we look at this equation again, d2r by dr square is minus lambda square d2r by d xi square. Then we have 1 over r is equal to j lambda by xi. Then dr is dr by d xi j lambda, okay, plus minus lambda square minus k square by r square. Okay, r square is j lambda square by xi square. Okay, so that into r, that is equal to 0. So I get a minus lambda square here. I get a minus lambda square here. Okay. If I take this minus lambda square out, okay, then I get a 1 minus k square by xi square into r, because I have a minus and a minus, I have a plus. Okay, so if I cancel out all the minus lambda squares, I get the same equation. Okay, so that is Bessel's equation. Okay, so what does it say? Let me copy it here. The equation looks like d2r by d xi square plus 1 by xi dr by d xi plus 1 minus k square by xi square into r is equal to 0. This is Bessel's equation, and its solutions are, for xi of the form lambda r, you get a j k lambda r and yk of lambda r. Okay, these are cylindrical Bessel functions of the first and the second kind of kth order. Okay, and for xi equal to j lambda r, you get ik of lambda r and kk of lambda r. Okay, and these are modified Bessel's functions of the first and second kind. Okay, and we said when the plate is closed in the theta direction, then k is an integer n, and therefore the total solution of R is a linear sum of all these solutions, which is C j n of lambda r plus d I n of lambda r plus e y n of lambda r and f k n of lambda r. Okay, so now what happens? The yn and the kn are singular, that means they blow up. They are singular, they go to infinity if r is equal to 0. So that means in the plate, if the origin is included, the plate includes the origin, it is not some annular region. Okay, it's not an annular plate, then yn and kn blow up, which means, okay, from a realistic engineering standpoint, E and F have to be 0. Okay, now please don't confuse that this is a number which becomes n. Okay, so that is the number k which became n, whereas this k is the Bessel function name, just as j, y and ik. Okay, so please do not confuse. So this, okay, that k as it became integer, it brings about the order over here, order number here, okay, for various k values. Okay, so now, so therefore we will now look at a case where we have a circular plate. Okay, it is closed in the theta direction, closed in the theta direction, which means k must be an integer n, and origin is included. Origin is part of the domain. Okay, so as a result, my solution is C times j n of lambda r plus d times I n of lambda r is r of r. That is the solution. Okay. Now, so we look at one particular case. Okay, we look at a clamped, okay, circular plate. And what does clamping mean? Clamping means the u3 at r equal to a for all theta for all time is 0. Okay, and this amounts to the r equal to a being 0. Then the slope del u3 by del r at r equal to a comma theta for all time is equal to 0, which means dr by d small r at r equal to a is equal to 0. Okay, so if we subject this to these two conditions, we get two equations. We get Jn of lambda a, In of lambda a, djn dr lambda a, din dr of lambda a C d equal to 0. So again, for non-trivial values of C and D, if this 0 has to hold, then the determinant of this matrix must be 0. Determinant of that matrix must be 0. That means Jn lambda a minus din by dr lambda a minus djn by dr, what is the product, this into this minus this into this. So djn dr lambda a into in lambda a must be equal to 0. Okay, so now this is satisfied by many lambda a's, many values of lambda a will satisfy this equation. Okay, so let's call them the mth order. So lambda a, the m values, m, let us say going from 0, 1, 2, okay, satisfy the equation, satisfy. And therefore, if we now remember lambda fourth as rho h omega square by d, okay, which means now my omega square is equal to lambda fourth d by rho h, and omega is equal to lambda square root of d by rho h, okay. Then if lambda a are paired together and I get the m values, this can be written as the lambda a m, okay, and already there is an n index because there is k has taken integer values, so we will put an n index also, that square by a square, because we have only lambda square here, square root of d by rho h, okay, and so this becomes omega mn. For every k equal to n, there are a set of lambda a values. So the lambda a come with the n index hidden, okay. So once I have lambda square, I write it as lambda a squared with index mn, but I remove the a in the denominator, okay. Now we do not like to keep derivatives in our equations, so we use identities, okay. So we have derivatives over here which we do not like, okay. So what we will do is we use identities which are a djn lambda a by dr, that can be written as n jn lambda a minus lambda a j of the n plus 1th order lambda a, then a times din by dr lambda a is equal to n in lambda a plus lambda a I to the power n plus 1 into lambda a, okay. So if this, the derivatives are replaced by this, what we get is now an equation jn of lambda a I n plus 1 lambda a plus I n lambda a j n plus 1 lambda a equal to 0, okay. Now once we found the lambda a of the mnth value, if we go back and put it in here, then the matrix becomes singular, so that any one equation is valid, okay. Only one equation is unique over here, so we get jn lambda a c plus I n lambda a d equal to 0. So this is what I mean by one of these being solved in terms of the other. So we will solve d in terms of c, okay. So d is minus c j n by I n, okay. So this d now is minus C j n lambda A by I n lambda A. Okay. So now if we write it up, what do we get? We get U r theta, which we had written as r of r into theta of theta. Okay. So that becomes now equal to C times j n of lambda r minus j n of lambda A by I n of lambda A into I n of lambda r, okay, into A cos n theta plus B sin n theta, or we can write this as cos n theta minus phi. Okay. So this becomes equal to C times j n lambda r minus j n lambda A by I n of lambda A, I n of lambda r cos n theta minus phi. Okay. So that's the mode shape, again unknown to the extent of one constant. Okay. So those now this is a mode shape, this is a mode shape r comma. Okay. So we have found the mode shape and the corresponding natural frequency. Okay. Now one thing is that unless the forcing is decided, unless the force is decided, okay, which way the mode will be oriented is not known, will not be known. Okay. Just as a mode shape, how a mode will be oriented will not be known, whether, you know, if a mode has two nodal lines, whether they will be like this or whether they will be a little more rotated, you know, will not be known. Okay. Only when there is a forcing, okay, in accordance with the forcing, the exact phi will be made clear. Okay. So we now have the mode shapes for a circular clamped plate. I will close the lecture here. In the coming class, I will start by showing the animations for this plate, circular plate. Okay. Thank you. I will close the lecture here.